Hello everyone, my name is Rafael Guzman Cabrera and I'm going to present the work Improved Approach to Wave Potential Estimation Using Biwave Distributions. This work was developed in collaboration between the Centro de Investigaciones Avanzadas Unidad Monterrey y la Universidad de Guanajuato, my colleagues Iván Xiomara and José Rafael. Data analysis is of critical importance in practically all areas of knowledge to support decision making. When the data are taken by acquisition systems and more than one variable is involved, it is common for the applied analysis to be statistical in nature. The analysis of experimental data collected at multiple locations over time leads to new and unique problems in statistical modeling and inference. The field of data fusion defined in a general way as the use of techniques that combine data from multiple sources, focus on the acquisition, processing, and synergistic combination of several sources of information, collected by one or more sources to provide a better understanding of the phenomenon to be considered. In this work, we propose a simple methodology based on the use of joint probability models that allow suppressing large amplitude fluctuations of the data caused by the extreme points while preserving the essential statistics. More specifically, we focus on a two-dimensional situation where two independent sensors report different variables over time in the form of ordered pairs with irregular activity. The methodology proposed is general and can be extended to other scenarios of two-dimensional data fusion where large amplitude fluctuations need to be reduced. Our proposal is illustrated for the practical cost of estimating the Z-wave potential. Relevance imputed to both global and in the Mexican context. Mexico has a coastline of 11,122 kilometers. Ocean energy technologies produce no emissions of harmful pollutants or greenhouse gases. Sea waves contain the highest energy density among clean and green sources.
No.
This picture clearly illustrates the problem at hand. By using the raw series of HMT pairs from the database, the wave power estimations end up spanning over several orders of magnitude, thus making it difficult to use these results for design purposes. In general terms, like we discussed in the introduction for other scenarios, this is because the fluctuations in the time series of each variable AHM of t and t of t are amplified through the calculation due to the nonlinear dependence of the wave power on these parameters. Pmax is highly proportional of AHM squared t cubed. In our approach, we essentially propose to use P of HMT of the raw data to generate a new series of random HMT pairs that are contained within an equiprobability constraint of P of HMT with a desired probability coverage. As we will show later, this approach is useful to generate a new time-scale independent series that preserves the probability of the measurements to the degree desired, and where the high variability due to the data fluctuations is suppressed. An overview of the proposed methodology is illustrated in Figure 3. In the following, the steps involved are explained in detail. An improvement over the previous approach is to model the joint probability distributions P of HMT by recognizing that AHM of t and t of t are not independent random variables. This is true for the time series HM of t and t of t explored in this work. In fact, the percent correlation coefficient between the year-long datasets shown is rather high, of R equal to 0.8389, which tells that there exists a strong linear dependence between HM and T. We plot the entire collection of HMT, first recorded over the course of 1 year, shows basically the same data where the time dependence has been removed. The algorithm for the generation of new HMT pairs based on the triangulation of the select contour is explained as follows. For each triangle, we determine its area and associate a probability based on its relative fraction with respect to the total area. Using this area-based probability, we pick triangles randomly and generate a random number inside of it. In this way, the region of the HMT plane within the equitable contour select is uniformly sampled. In practice, we did this in a fully vectorized manner to generate n samples in a single step. We show the result of the generation of n equal to 8,700 samples, a new data series of the same length as the original data. The results of the methodology proposed in the condensed form of a box plot representation, we plot the statistics of the original measurements and those of the randomly generated shown in the figure. The red markers indicate the outliers based on the standard criterion of the interquartile range, where Q1 and Q3 are the first and third quartile respectively. In table, we show a comparison of the calculation obtained using the raw data and the proposed approach. Basically, we calculate Pmax based on the Salter-Fallness formalism described above, when using a single HMT pair of the entire series for both the raw data and the generated series. Summary. Fusion of real-life noisy data that results in large fluctuations. C-wave power expression. Simple methodology based on joint probability distributions. Suppression of large fluctuations. Preservation of the main features of the original statistics. Core of the proposed methodology. Measurements of C-waves height, HM, and period T. Modeling the joint probability distribution phi of HMT. Use an equiprobability concept to generate new random HMT pairs. Outcome. Fluctuation suppressed data with preserved core statistics. Realistic data generation using phi of HMT from measurements. New data independent of a time scale. Useful data for numerical simulations and device design. Okay, that's all. Thank you for your attention and see you soon.